Welcome to The Explainer. Today, we're jumping right in to demystify a truly foundational framework in software engineering, the unified process. We're going to look at exactly how you get from a vague, messy set of business requirements to perfectly aligned deployed code. By the end of this, you'll see how this methodology creates the kind of transparent insight you need to guarantee clear alignment and total stakeholder trust. Because today, especially as we're connecting complex systems to powerful AI models like Claude, having a rigorous, transparent blueprint isn't just a nice-to-have best practice. It's absolutely essential for building ethical systems we can actually trust.
Okay, let's dive into this syllabus. We're going to start off by looking at the 1970s software crisis. Then we'll meet the unified process itself, decode business intent with lexical analysis, visualize our architecture using UML diagrams, and finally, we'll prove our execution with the traceability matrix.
Part 1. The 1970s Software Crisis.
Now, to really appreciate why the unified process is such a game changer, we kind of have to rewind to a time when software was failing faster than it could even be written. So, why did these massive 1970s software projects fail so spectacularly? Well, it wasn't because the code was technically bad. The real villain here was misalignment. See, in the early days, business analysts often just wrote the code themselves. But by the 70s, professional programmers took over. And the problem? Those programmers usually didn't understand the business domain. We basically let people who had no idea how a bank or a warehouse actually worked design the requirements for the systems they were building. It was this unstructured ad hoc craft, and honestly, it led to total chaos.
To put the scale of this disaster into perspective, just look at IBM's legendary OS360 project. As hardware capabilities scaled up, the software trying to run on it became this tangled, unmanageable mess. The project ran an estimated 200% over budget. That is wild. And this wasn't just an isolated IBM problem. It was a global crisis. The systems technically worked according to a compiler, sure, but they absolutely failed to deliver what the business actually needed to survive.
If we track this crisis on a timeline, you can see the industry's desperate reaction. In 1968, NATO actually held a conference specifically to address this mess. That's where the term software engineering was coined. Thinkers like Frederick Brooks started arguing that we desperately needed the same rigor and discipline you'd find in traditional civil engineering. And so, by the 1980s, the unified process finally emerges to inject that much-needed predictability and structure into the world of code.
Which brings us to Part 2. Meet the unified process.
Let's move to and see how this builds step by step. The tactical workflow of the unified process is a very deliberate six-step journey. We start out by gathering user stories from our stakeholders. Then, we transform those stories into a formal requirements document filled with shell statements. Exact definitions of what the system shall do. From there, we discover use cases, which are the core algorithms of the business. Next, we model the whole thing out with UML diagrams. Once that model is perfect, we forward generate our code and database schema. And finally, we build the traceability matrix to prove we did exactly what was asked.
And this brilliantly illustrates the whole concept. Think of the unified process like a giant pasta maker. Your requirements, representing the complex business domain, are the raw dough that you feed into the machine. Turning the crank, that represents working through the steps of the unified process we just talked about. And what comes out the other side is functional code in a database schema, perfectly shaped and totally ready for deployment.
Part 3. Decoding with lexical analysis.
Okay, so you might be wondering, how do we actually get from a paragraph of text to a concrete piece of data? We do it through a technique called lexical analysis. This is the bridge that transforms abstract intent into concrete architecture. And here is the absolute golden rule you need to anchor in your mind right now. Nouns become data fields and verbs become methods. By identifying the entities, the nouns, in our use cases, we map them directly to data attributes. And by identifying the actions, the verbs, we map them directly to the methods in our object architecture.
Let's ground this in reality for a second. Imagine we're modeling a library system. We've gone in, interviewed the librarians, and gathered our user stories. Now we just apply our lexical analysis to discover the objects and behaviors hidden right there in their description of a typical day at the library. We look at the domain and simply pull out the nouns: book title, ISBN number, and author name. Boom! Those instantly become our data fields. Then we look for the verbs: borrow book and return book. There are your methods. We aren't just sitting around guessing what the system should do, we are literally extracting it directly from the business domain itself. But once we have all these fields and methods, who actually owns them? Well, this is where we apply responsibility-driven design to something called the knowledge principle. It basically states that the object that knows the most about a business process is the object that should be in charge of it. It's a simple rule, but it ensures we get high cohesion and low coupling. Basically, it guarantees our code is organized logically, so data and behavior are living together in the most sensible way possible.
Moving on to part 4, visualizing with UML diagrams.
Now, what's really interesting about this slide is seeing how the logic evolves visually. Once we have our elements and responsibilities assigned, we graph them out. On the left, you see a standard activity diagram splitting flows conditionally, like deciding between overnight or regular delivery, and then merging back together. But on the right, we have a swim lane layout. This groups activities by the actor or component performing them. It shows exactly which part of the system is doing what. And let me tell you, that is a vital level of transparency for building stakeholder trust, especially when these components are interfacing with modern AI controllers.
And remember, UML isn't just some static drawing on a whiteboard. We use it for round-trip engineering. That means we forward-generate our Java or Python code directly from these models. But the cool part is, it goes both ways. If a developer finds a better way to write an algorithm while they're deep in the implementation phase, we backpropagate those changes right back to the UML. It's a brilliant feedback loop that keeps the design and the reality of the code in perfect sync at all times.
And finally, part 5, proving it with the traceability matrix. We've reached the grand finale. The system is built, but how do we actually prove that it works? Enter the traceability matrix. It's essentially a giant grid. You list your shall statements from the requirements document right down the rows and your programmatic methods across the columns. Wherever a method helps deliver a requirement, you just put a checkmark. Each checkmark becomes a test case. This is exactly how you visually assure stakeholders that every single requirement has been addressed by a specific piece of code.
So the crucial point is that the traceability matrix is the ultimate bridge between business intent and deployed execution. It provides a level of transparency that, quite frankly, is pretty rare in modern development. When you're connecting highly complex systems to AI models like Claude, this matrix is how you prove your system is doing exactly what it's supposed to do, and maybe just as importantly, doing absolutely nothing it isn't supposed to do.
This visual mapping guarantees 100% test case coverage. It completely moves us away from the old, just trust me, I'm a programmer mindset, and moves us directly toward, here is the hard evidence. This is exactly how you achieve complete stakeholder buy-in and build a system that is fundamentally rooted in transparency and ethical design.
I'll leave you with a provocative thought to chew on. Take a look at your own code base today. Does it have dead execution paths? Methods that aren't actually tied to any real user requirement? Without the unified process, it's almost impossible to know for sure. Thanks for joining me to explore how we turn complex problems into traceable, reliable solutions. I'll catch you in the next explainer.